Okay, we're at 17.4 waves under boundary conditions. Um, and they're going to show here a taut string. You can imagine a string anchored on like a guitar string or a piano string or a harp. I think a harp would be a good one to imagine because it has very visible uh, length differences. The piano does too, but they're kind of hidden behind the piano cover. Uh, so we have here a length L with a taut string anchored at both sides. We call the left side x equals 0, and on the right side x equals L. So the length of the string is L, um, and the frequency the uh, frequencies that it generates, the wavelength of the frequencies that it will generate is twice the length divided by n, where n is equal to 1, 2, 3, and 4. So by its nature, the fact that it's anchored on both ends, nodes will have to appear at the ends. In other words, the string's not free to move at the end, so it's going to have to be a node. It's going to be anchored there. So the fundamental, or the first harmonic, is given is shown here, where you have a node at either end and you have an antinode. So n equals 1, so the length is equal to 1/2 uh, lambda 1. In other words, it's a half wavelength. Um, at the second harmonic, n equals 2, you can see you have, of course, a node at either end, then you have a node in the middle, and you have antinodes on either side. Now, this is a full wavelength from the upgoing zero crossing, I'm going to call it, uh, a downgoing zero crossing, then back up to a upgoing zero crossing. So this is the second harmonic. The length is equal to the lambda of the second harmonic, and it's going to be twice the frequency of the fundamental. And then the third harmonic, n equals 3, you have uh, 1, 2, 3, 4 nodes and 3 antinodes. And so n equals 3, and L is equal to 3/2 lambda 3 for the third harmonic. So lambda, the wavelength, is equal to 2L twice the length divided by n, where n is the number of, in this case, the number of antinodes. Um, uh, and so the velocity is equal to lambda times frequency. Rate equals distance divided by time. Lambda is the distance. Time is the what is period. What is what is did I say that right? Velocity. The rate velocity is equal to distance divided by time. Uh, the velocity is the speed of sound. Lambda is the wavelength, and the frequency is 1/t. So it's distance divided by time. The frequency is equal to the velocity divided by lambda, is equal to the n, where n equals 1, 2, 3, times the velocity divided by 2L. And we've also learned that the velocity is equal to the square root of the tension in the string divided by the linear mass density. The so if you increase the tautness, if you increase the tension in the string, the velocity goes up, not linearly, but by the square root. If you increase the mass density, the velocity goes down, and that's why the bass strings are a thicker. Uh, there's more mass density to the bass strings of a guitar or a piano. You increase the mass density, the velocity goes down, the tone goes lower. Okay, the f of n is equal to n 2L times the We're substituting, we're taking that top equation and we're substituting um, T over mu for the V. So the frequency is equal to N over 2L times the square root of the tension divided by the linear mass density. And so for the fundamental for F1, N equals 1. So F1 equals 1 over 2L times the square root of the tension divided by the linear mass density. Let me catch up with my notes. So the this goes back to the opening uh, picture with Jack White of the, I already forgot what they were called, the White Stripes, I think they were. Um, and you can, if you just pluck on a string, you get the fundamental, but you can generate overtones. You can, depending on where you put the your finger. Uh, the the when you place your finger lightly at the midpoint, the entire string can still vibrate when you pluck it, but your finger imposes a node at the center of the string. The fundamental node of vibration is n equals 2. The harmonic of an open string, the frequency is twice as high. It's an octave when you put it at the center. You can tighten that. You can, with the little screws, you can tighten the tension in the string and raise the frequency, or loosen it and you lower the frequency. I'm not a musician, so I don't play with guitars much, but I'm sure one of some of my students probably know how to play a musical instrument, and they're familiar with all this. All right. Let's look here. When a standing wave is set up on a string fixed at both ends, which of the following statements is true? The number of nodes is equal to the number of antinodes. Um, well, we know that, let's just take the fundamental. You've got 2 nodes and 1 antinode, so they can be equal. The wavelength is equal to the length of the string divided by an integer. Well, that's not right. The That's only true for half of the modes that you have. It's not true for any odd numbered mode. The frequency is equal to the number of nodes times the fundamental frequency. That would be correct if we replace the word nodes with antinodes. Because remember, the fundamental, you have 2 nodes and you have 1 antinode. So that would be F1. But that's only true if we were to replace the nodes with the word antinode. The shape of the string at any instant shows a symmetry about the midpoint of the string, and that we know is true. So that's the answer to that quick quiz. So we show here the 3, the first harmonic, the second harmonic, and the third harmonic, and we know that that this is, these are waves under boundary conditions, and this happens when a wave is traveling back and forth on a guitar string combined to form a standing wave. Sound waves traveling back and forth on a clarinet combined to form standing waves. A microscope particle confined to a small region of space is modeled as a wave and exhibits quantized energy. The Fermi energy of a metal is determined by modeling electrons as wave-like particles in a box. So that ends this section, and next we're going to go to resonance.